Chapter 21: Reactor Safety and Security. It is well known that the accumulated fission products in a reactor that has been operating for some time constitute a potential radiation hazard. Therefore, assurance is needed that the fuel integrity is maintained throughout the operating cycle, with negligible release of radioactive material. This implies limitation on power level, temperature, and adequacy of cooling under all conditions. In this chapter, we will examine the precautions taken to prevent release of radioactive material to the surroundings and discuss the philosophy of safety. This chapter will also examine 3 well-known nuclear power plant accidents, which are 3 Mile Island, Chernobyl, and Fukushima. Section 1: Safety Consideration. Preventing the release of radioactive material then becomes a fundamental goal, as the majority of the radionuclides are present within the fuel. The basic strategy is to preclude fuel overheating. Preventing fuel from melting is not the sole consideration. In water-cooled reactors, the cladding is normally made by zinc alloy. The elevated temperature can lead to phenomena such as the exothermic zirconium water reaction. As shown by this formula, Zr plus water will give you ZrO2 and hydrogen. This reaction will release the heat and make the things worse. In addition, it will release the hydrogen and give you a potential explosive hazard. So beginning around 1600 Fahrenheit, which is around 900 Celsius, this cladding oxidation turns the ductile zirconium into a brittle ZrO2. So for each kilogram of Zr, the reaction yields half cube meter of hydrogen and 6,500 kilojoules of heat. In addition, the Code of Federal Regulation acceptance criteria for emergency core cooling system for light water reactors states that the calculated maximum fuel element cladding temperature shall not exceed 2200 Fahrenheit. Section 2: Assurance of Safety. The systems by which safety is assured can be categorized into 3 types. A. Inherent, based on intrinsic physics principles. B. Passive, does not require active initiation or power. C. Engineered, power operated and must be activated. Examples of this safety mechanism include negative reactivity feedback. This is inherent. It is built into the physics. Natural circulation and gravity-fed cooling. This is passive. This one does not require any external power. And also digital reactor production systems and emergency diesel generators. So these engineers require either fuel or electricity. To enhance safety, newer reactor designs have sought to replace engineered systems with inherent and passive features because we believe that A, inherent, and B, passive, are more reliable than the engineered system, which require external power. Because almost all the reactivity generated by a reactor appears in the fuel element, great precautions are adopted to ensure the integrity of the fuel. This includes 2 parts. The first one is the fuel, and the second part is the cladding. So the fuel are made to have identical chemistry properties with the same size and the same shapes. For the cladding, it must be strong enough to hold all the fission fragment and also withstand the high pressure from the coolant. The cladding material usually selected for low neutron absorption and for resistance to chemical action, melting, and radiation damage in small reactor. So normally it is made by zinc alloy. It is an alloy that is approximately 98% zirconium with a small amount of other metals. In addition, each reactor has a set of specific limit on operating parameters to ensure protection against the events that could cause hazard. This will include upper limit on total reactor power, which determines temperatures throughout the core. Another is the ratio of peak power to average power that is related to hot spots and fuel integrity. We prefer that the reactor power distribution is flat, so you do not have a very hot spot at a certain location. Protection is provided by limiting the allowed control rod position as well. At last, the coolant flow has to be maintained above a certain level in order to ensure enough cooling to the core to prevent the core meltdown. In section 3, we just need to know that in United States, the Nuclear Regulatory Commission, NRC, has the authority to license and regulate the nuclear facilities of all types. And the Code of Federal Regulation Title 10 Energy, 10 CFR 50, provide the basis for issuance of a construction permit and later, when the plan is completed, an operating license. In addition, the NRC is also a primary funder of our nuclear program. Section 4, Emergency Core Cooling and Containment. The design features and operating procedures for a reactor are such that under normal conditions, a negligible amount of radioactivity will infiltrate the coolant and find its way out of the primary loop. Knowing that abnormal conditions can exist, the worst possible event, called design basis accident, are postulated. The engineered safety features, such as core cooling, containment, and control room habitability systems, consist of backup production equipment provided to render the effect of an accident negligible. A loss of coolant accident, LOCA, is one condition typically assumed, in which the main coolant piping somehow breaks, and thus the pumps cannot circulate coolant through the core. Although in such a situation, the reactor power would be reduced immediately by use of control rods, so the reactor will be shut down quickly. There is a continuing supply of heat from the decaying fission product that would tend to increase temperatures above the melting point of the fuel and cladding. In a severe situation, the fuel tubes would be damaged and a considerable amount of fission product released. To prevent melting, an emergency core cooling system, ECCS, is provided for water-moderated reactors, consisting of auxiliary pumps and inject and circulate cooling water to keep temperature down. In other words, after the reactor is shut down, the reactor will continuously provide or generate heat through radioactive decay. Therefore, continuous cooling must be provided to cool the reactor core to prevent the overheating. Section 4. Emergency core cooling and containment. In this section, we are going to study the most important safety system that is only activated under accident condition to ensure the core continuous cooling. This system is the emergency core cooling system, or ECCS. Before that, let's first review the pressurized water reactor configuration. So the basic pressurized water reactor (PWR) system includes the reactor vessel, which is at the center of this figure, and the primary coolant pump, which will keep the coolant flow, which is at the lower right corner, and also the steam generator, which serves as a heat exchanger to reject the heat from the primary loop to the secondary loop in order to produce the steam. You'll see that the reactor pressure vessel, the core, and the pump, and also the steam generator, and also all those piping are located inside this reactor containment building. We show in this figure some of the equipment that constitute the engineered safety features. The first one is the high pressure injection systems. The high pressure injection systems is labeled as HP, which stands for high pressure. This high pressure injection system goes into operation if the reactor vessel pressure drops from a normal value of approximately 20 to 50 psi or 155 bar to approximately 1500 psi or 100 bar as the result of a small leak. If you have a small leak, then the pressure will decrease gradually. Then, after this system is activated, the water is taken from the buried water storage tank, which is shown to the right of this figure, and introduced to the reactor through the inlet cooling line. Okay, so the water will be taken from this storage tank and pumped by this high pressure injection system pump, then injected to the core to maintain the core water level and also the pressure. The next one is the core flooding tank, which is shown here. Okay. This is also called the safety injection tank. This core flooding tank can deliver buried water to the reactor through separate nozzles in the event of a large pipe break occurs. Such a rupture would cause a reduction in vessel pressure and an increase in building pressure. When the vessel pressure becomes approximately 600 psi or 40 bar, the tank check valve opens and water is forced into the core through nitrogen pressure in the tank. So this one uses the compressed nitrogen, and it does not require the electricity to operate. So after the high pressure injection system, and if the pressure continues to drop, then later this core flooding tank will be activated. Then, if the primary loop pressure continues to fall to approximately 500 psi or 35 bar, then the low pressure injection system, which is labeled as LP for low pressure, as shown here, The low-pressure injection pump starts to transfer water from the same buried water storage tank to the reactor. The refilling water storage tank typically serves as a large reservoir of buried water. When this tank is nearly empty, the pumps take spilled water from the building sump as a source and continue the flow through coolers that remove the decay heat generated from the fission product. You see that there's another line. It can take the water from the bottom of this contaminated building and recirculate and reuse those cooling water. In the case that this storage tank water are all used up. Another feature is the containment spray system. This one goes into operation if the building gauge pressure increase above approximately 4 psi or 0.3 bar. It can take the water from the buried water storage tank. It can take the water from here and discharge it from a set of nozzles located above the reactor to provide a mean for condensing steam in the containment atmosphere. At the same time, the emergency cooling unit of the reactor building are operated to reduce the temperature and pressure of any released vapor, and the reactor containment isolation valves are closed on unnecessary piping to prevent the spread of radioactive material outside the structure. The emergency core cooling systems, ECCS, must be capable of limiting the surface temperature of the colloid cladding to specified value, for example 2200 Fahrenheit, of preventing significant chemical reaction, and of maintaining cooling over the long term after the postulated accident. The role of the steel reinforced concrete reactor building, or this containment building, is to provide containment of fission products that may be released from the reactor. It is designed to withstand the internal pressure and to have a very small leak rate. In addition, the reactor building is located within a zone called an exclusion area of a radius of the order of half a kilometer, and the nuclear plant site is several kilometers from any population center. We can estimate the magnitude of the problem of removing fission product heat. So here, I neglect the derivation steps. If you are interested in this derivation, you can look at the textbook, page 394. Okay. I will just show the final formula. So the empirical formula for calculating the reactor decay power, here when we are talking about the decay power, it is always the thermal power. So the reactor decay power after shutdown can be estimated by this formula. In this formula, the P bracket T is the reactor thermal power after T seconds. Okay. So you want to estimate, for example, 1 hour after shutdown, then this T will be equal to 3600 seconds. The P0 is the reactor power before shutdown. So if you operate this reactor at a higher power before shutdown, then at the later time after the shutdown, you get also higher power because you have a more fission product produced. And the capital T is the reactor operating time before the shutdown. Both the lowercase t and the capital T are in the unit of seconds. Okay. Then, if this t is very large, if the t is means that if the reactor has been operated for infinite amount of time, then the second term inside this bracket can be neglected. In that case, we will have this simplified equation. So Pt will be equal to P0 times the factor 0.07, then times t to the power of negative 0.2. Okay. Then we can show this power in this figure. Okay, this figure. And you will see that this power is reducing, okay, but still it will give you a lot of heat right after the shutdown. Therefore, the cooling must be maintained. Now let's look at the example 21.2. After operating for an extended period before shutdown. Extended period means that we assume that this reactor has been operated for a very long time or infinite amount of time. We can calculate the reactor power 10 seconds after shutdown. Okay, so we use this equation, and in this equation, we'd like to calculate what will be the percentage of the power 10 seconds after the shutdown. In this equation, the only variable will be the t and the p0. Okay, t and the p0. So 10 seconds after shutdown, so we replace the t by 10. Remember that this t must be in the unit of second, always. So here, the 0.07 times 10 to negative 0.2 will be 0.044. So that is, it means that 10 seconds after the reactor shutdown, you have the thermal power of 4.4% of your full power before shutdown. Okay. Next, we will calculate the percentage for 1 day. Okay, percentage for 1 day. And by the end of this day, means that 1 day after the reactor shutdown, you need to replace this t by the number of seconds in 1 day, that is 24 times 3600. Then the result will be 0.72%. Okay, so the power will be reduced to 0.72%. This value looks low, but if you have a very big reactor, 0.7% of your full power is still lots of heat. For example, if we consider a typical reactor which has a thermal power of 3000 megawatt thermal, then by using this formula, we replace the P0 by 3000 megawatt thermal and replace the lowercase t by 24 hours times 3600 seconds per hour. Then we can get a 21.6 megawatt thermal. So this is still a very large amount of heat power you have to remove by the end of 1 day after the shutdown. Section 5, Probabilistic Risk Assessment. The probabilistic risk analysis or assessment, aka PRA, is a formal method for analyzing reactor systems. The objective of this method is to find the chance of an undesired event, such as core damage, breach of containment, or release of radioactivity, and to determine potential causes. The first step is to investigate all the possible faults in the equipment or process. Flow diagrams of fluid systems and the circuit diagram of electrical systems serve as a reference. In general, we have two types of trees to analyze the system. One is called the event tree, another one is called the fault tree. The event tree are logic diagrams relating an initiating event to either successful mitigation or failure. This figure shows a simple event tree. So let's first look at this event tree. At the beginning, you have the initiating event A. This initiating event can be pipe break. For example, you have a break to your mine coolant pipe, and you will lose a lot of coolant. At that time, after this event, you are going to determine if you still have the reactivity control. Means that if you can shut down the reactor or not. And to going up, that is success. Going down, that is failure. For the reactivity control B, if you still have the control to shut down your reactor, then means that it is successful. Then you can go to the next step. Otherwise, if the reactor fails to shut down, then apparently the plant will be damaged. So if you have the failure to the reactivity control B, then you will see that the consequence 6 will be the plant damage. After your reactivity control B, you need to apply the cooling because you lose lots of coolant. And that will call for the high pressure injection system C. If the high pressure injection system C success, and you will continue, and gradually your core pressure will be reduced. In that case, you are going to call for the low pressure injection system. And the low pressure injection system is also bounded with this decay heat removal. And if that is successful, that means that you have the consequence 1A, and you have success, and your core is safe. Otherwise, your core will be damaged. In addition, if your high pressure injection system fail to start, and later your reactor pressure is going to reduce to the set point for the low pressure injection system. And after that, we are going to determine if the low pressure injection system is successfully activated. If that is not activated, then you have the 5 plant damage. And after it is activated, and we check to see if we have the continuous decay heat removal system operable. And if that is successful, then we will have the 3AC success. Otherwise, we have the consequence fall and full plant damage. So we see that from this fault tree, from this event tree, we will be able to understand and study what will be the consequence for certain failure of certain safety systems. Next, we are going to look at the fault tree. Probabilities of success and failure at each branch are applied. The principal logic diagrams are the fault trees, which trace causes and effects mathematically by use of Boolean algebra, which is a form of set theory. Now let's look at this figure. Figure A shows a simple high-pressure injection system to which we can apply the concept for this illustration. And this figure A is cooling to the reactor, and the cooling water is provided by the 2 pumps and also the valve. We can simply see that the failure of both pumps, if both pumps fail to start, or the failure of the valves, if the valves fail to open, prevents cooling water from reaching the reactor. Then, based on this system, we can construct figure B, which is a fault tree diagram. In this fault tree diagram, you see that we have 2 types of the gate. One is called the OR gate. Another one is called the AND gate. And in the next page, we are going to have a detailed discussion about these two gates. For the AND gate, it requires that both event or two or more events all failed to produce the failure of this branch. The OR gate only requires one of the event to fail in order to trigger the failure of the upper branch. The first one is intersection. So we have A and B in parallel connection, as in the previous two pumps are connected in parallel. And in that case, if one pump successfully starts, you will have the water flow on the right-hand side. Therefore, we only need one or both pumps to operate. So A and B will be, the relationship will be AND. And to make this entire system fail, you need to have both pumps or all the subsystem fail. Therefore, for this AND gate, the output is fault if all the input events are fault. Or we can see that from this Venn diagram is that we are trying to calculate the area between these two circles. Okay, means that you need to have both systems fail. So we use A times B to represent the intersection or the AND. Then the probability will be PA times PB. For example, if you know the failure rate for A, failure rate for the B, then the probability for this parallel connection will be PA times PB. In other words, this intersection means you have a parallel circuit of two components. Then the system fails only when both subcomponents fail together. Then you have the entire system fail. In other words, all fails, then the system fails. So this will be the AND relationship. So the example is that the pressurized water reactor is supported by two independent RHR systems. You have a core meltdown happens only if both systems fail to start. Okay, both systems fail to start. And pay attention to the shape of this AND gate. So you have the flat at the bottom, okay, flat at the bottom, and round head on the top. Okay, it's round on top. So this is your AND gate. Next one, we talk about a different connection, that is serial connection. The Boolean operation is union, or in this gate, we call it the OR gate. In the previous example, we have the pump serially connected to this valve. So the water will flow through the pump and also flow the valves later. And to cause no flow to the right-hand side to this reactor, either pump fail or the valve fail. So you have one or more subsystem fail will cause the total entire system to fail. So this OR gate tells us that the output is fault. Only the output is fault if one or more input event occurs. Okay, if one or more input event are fault. So we call it union. From this Venn diagram, we are trying to calculate the total area of these two overlapping circles. Therefore, the probability will be the PA, which is the left circle area, plus PB, the right circle area, minus PA times PB, minus the intersected area, because we counted this intersected area twice, so we minus PA times PB. And for the union, we use the plus sign, so A plus B. And the union means that you have a serial connection of two or more components. Okay, either one fail will lead to the failure of this branch of the fault tree. In other words, one fail, the system will fail. So that is the union. We have another example. So we have two valves are mounted along the same pipe. Then the control system sends a signal to both valves and ask both valves to open. If one of them fail to open, then there will be no water flow in this pipe. So one fail, the system fail. And normally the PA and PB, they are both small numbers. Okay, then PA times PB is an even small number. Therefore, sometimes we can apply this rare event approximation. Because the failure rate is small, then we can ignore the value of this PA times PB. Okay. Therefore, if we apply this rare event approximation, then the failure rate for this union system will be PA plus PB. Okay, just PA plus PB. Sometimes we may have a 3 component in serial connection. Okay, in that case, we have PA plus B plus C. Okay, so A union B union C. We are trying to calculate this area occupied by these 3 circles. Okay. Then by applying this rare event approximation, we can just say that the PA plus PA plus B plus C will be equal to PA plus PB plus PC. Okay, now let's recall that PA and B, you get PA times PB. Then PA or B is equal to PA plus PB minus PA times PB. So this is these two are the two fundamental probability equation. Okay. Now let's attach the symbol to those events. So we have the A, that is pump 1 failed to run. We have the B, pump 2 failed to run. And from this system configuration, we determine that they are the relationship, they are the AND. Okay, so we use the AND gate to connect them together. Then, if this one fail, what we get is the pump failure. That is F. That is F. Then pump failure and the valves, they are in serial connection. Okay, in serial connection. So we have the OR gate. Okay, OR gate. And if either valve fail or pump fail, then you get no flow to this reactor. Okay, to this reactor. Therefore, as shown here, so the F is equal to A and B. Okay, F is equal to A and B. And the T, no flow to the reactor, is equal to C or B. C or B. So apparently C and F, apparently the F is not the basic event. Okay, because we assume that the basic component failure is the basic event. So pump fail or valve fail, that is the basic event. So we are going to perform some derivation to the next slide. So PT, that is the top event, is equal to C union F, C or F. Okay. Then from our equation, PC or F is equal to PC plus PF minus PC intersect F. Then we know that F is equal to A and B. Therefore, replace all the F by A and B. So we will have this the third formula. Okay, third formula here, third bullet point here. So we replace the F by A and B. So PF will become the PA times PB. PA times PB. So the third term will be PC times PF. Then PC times PF will become PC times PA times PB. Okay. So we have this final equation derived. Then we'll take this example 21.3. Now we will have the event probabilities. So we assume that the PA is equal to PB is equal to 10 to negative 3. This one means that if you call for this pump to operate, it will have one failure per 1,000 call for the pump failure. And PC will be the valve, that is 10 to negative 4. Then this PT will be equal to PC, that is 10 to negative 4, plus PA times PB. So because PA and PB, they are both equal to 1 over 1,000. So you get the 0.001 square minus the PC, which is 10 to negative 4, then times PA times PB, which is another 10 to negative 3 square. Then we get 1.01 times 10 to negative 4. So this shows that the top event is dominated by the possibility of the valve failure. Okay. And also the product of 3 probabilities can be neglected, assuming this rare event approximation. Although duplicated systems render nuclear power plant more expensive, redundant equipment is employed extensively because safety considerations are paramount. For instance, the Code of Federal Regulation requires that each nuclear reactor must be outfitted with 2 independent systems to shut the reactor down, and one of the 2 systems must use control rod. The ultimate objective of PRA is to estimate risks to people, calculated by use of a principle most simply stated as risk is equal to frequency times consequence. For reactor, the frequency means the number of times per year of operation of a reactor that the incident is expected to occur. And consequence include the number of injuries or fatalities, either immediate or latent, as well as property damage. The technique of PRA is used to determine which changes in equipment or operation are most important to ensure safety and also give guidance on emergency plans. Now let's move to example 21.4 to show how to use this simple equation. In 2009, the US Census Bureau reports that 10.8 million motor vehicle accidents with 35,900 resultant deaths. The number of deaths per accident can be calculated by this simple formula as well. So it is very simple. So that is the total number of deaths per year divided by the total number of accidents per year. Then it will give you 0.003 deaths per accident. In other words, for every 1,000 accidents, there are 3 deaths. Then we can also calculate the individual risk. Consider a national population of 0.31 billion people. Then the individual risk will be number of deaths per year over total number of population. This will give you 1.17 times 10 to negative 4 deaths per person per year. In other words, for 10,000 persons, there is one death from vehicle accident per year. Next, we will talk about 3 major reactor accidents around the world in human history. The first one will be the 3 Mile Island accident. It is rated as level 5 accident in the International Nuclear Event Scale. This NES, the worst accident, is rated as level 7, and the 3 Mile Island is rated as level 5. It caused significant damage to the nuclear device, but the release of radioactive material to the surrounding area is not very large. So the date is in 1979 in Pennsylvania, United States. The ultimate cause to this accident include the violation of safety protocol, human errors, and also the mechanical failure. This accident caused the core partial meltdown, and this is permanent non-repairable damage. The reactor has to be decommissioned. The release of radioactivity to the environment or to the people is minimal, and there's no deaths or injuries. So this nuclear power plant, belongs to Exelon Nuclear Company. Exelon only uses the nuclear power to produce the electricity. The 3 Mile Island power plant has 2 reactors, and they are designed by the B&W. Each reactor is able to produce 650 megawatt electricity. The Unit 1 is still operational until today, but Unit 2 has been decommissioned. So this 3 Mile Island nuclear generating station is a nuclear power plant located on this 3 Mile Island in this river close to Harrisburg, Pennsylvania. This island is about 2 miles long. The name comes from the distance because this island is 3 miles from the middle town of Pennsylvania. And to the right figure shows the top view of this island and also the power plant. You will see that half of this island is occupied by this power plant. The left figure shows a closer look. You see that there are 4 cooling towers, and each reactor will use 2 of them. And the 2 of the cooling towers are being used by the Unit 1, but the other 2 cooling towers are not being used because the Unit 2 has been decommissioned. In 2010, the population within 10 miles is 211,000, and the population within 50 miles is nearly 3 million. And you can see that this power plant is located in a dense populated area, and anything happen to this power plant may have a significant consequence. To understand the accident consequence, let's first discuss about this pressurizer. This pressurizer is only used by the pressurized water reactor. It is not used by the boiling water reactor. This pressurizer is the component in the reactor coolant system, and its purpose is to control the primary loop pressure. This pressure is controlled using electrical heater, pressurizer spray, power-operated relief valves, and also the safety valves. The figure shows the basic configuration of this pressurizer. So the pressurizer inside is filled with water and steam. So the water is filled halfway through this pressurizer. So at the bottom, it is filled with water, and it is connected to the pressurized water reactor primary loop. And on the top, it is filled with steam. So inside this pressurizer, it is saturated mixture, okay, saturated water mixture. So the water and the steam are in equilibrium. If pressure starts to deviate from the desired value, then different components will automatically activate to bring the pressure back to the normal operating points. The cause of the pressure deviation is normally associated with the change in the temperature of the reactor coolant system. So if the reactor coolant system temperature start to increase, then the water is going to expand, and the more water will come into this pressurizer and compress the steam in the upper region of this pressurizer, ultimately causes the entire primary loop pressure to increase. Okay. So if the temperature is increased, then ultimately the pressure will increase. On the other hand, if the reactor coolant system temperature decreases, then the water is going to contract. Then the water will flow out of this pressurizer back to the primary loop. In that case, the steam region will occupy more space. In that case, the pressure is going to decrease. So you have lower temperature of the coolant, then you have lower pressure. For either pressure increase or decrease, the pressurizer will operate to bring the pressure back to the normal. For example, if the pressure start to increase, and on top of this pressurizer, you see that there's a nozzle. Okay, there's a nozzle, and this spray line will allow relatively cold water from the discharge of the reactor coolant pump to be sprayed into the steam space. And here in this steam, it is maintained at a relatively higher temperature than if you spray the cold water into this steam. You are going to condense some of the steam back to water. If the steam is condensed to the water, then it will occupy less volume. In that case, the pressure is going to be decreased. Then, if the pressure continues to increase, then on top of this pressurizer, there will be different valves. Okay, different valves. Then the pressurizer relief valves will open and dump the steam to the pressurizer relief tank. Okay, will dump the steam to this relief tank. Inside this relief tank, it is filled with cold water. Then steam in contact with this cold water will be condensed, so that the primary loop will be discharged, and the temperature and the pressure will be maintained. If the pressure starts to decrease, on the other hand, for some reason, if the pressure starts to decrease, then we are going to automatically turn on this heater. Okay, turn on this heater. Then if this heater is turned on, it will boil more water to steam. And the more water is boiled to steam, then steam is going to compress this steam bubble and increase the pressure. If the pressure continues to decrease and reach another predetermined set point, then the reactor protection system, like the emergency core cooling system, will automatically start and also the reactor will be shut down. This figure shows two real-world pressurizer. The top one is the Areva EPR reactor pressurizer. The bottom one is Westinghouse AP1000 pressurizer. Okay. You will see that they are big equipment. Now let's look at the 3 Mile Island accident. This figure shows the diagram or the configuration of the 3 Mile Island reactors. At the center, it is the primary loop or the primary coolant system. You have the reactor, steam generator, pressurizer, and some safety system. On the right-hand side, it is the turbine building. You have the steam will rotate the turbine and the generator to produce the electricity. Then it will be condensed, then sent back to this steam generator. To the left-hand side, it is some safety system. So we are going to talk about that later. At the beginning, so that is 4 a.m. on March 28, 1979. This reactor was operating at 97% power when the steam generator main feed water system malfunctioned, causing the turbine generator to trip. It means that for some reason, the turbine is offline. So the real reason was that some instrument malfunctioned. Then, if the turbine is offline, we should have the backup feed water system to provide the cooling water to this steam generator secondary loop side to provide as heat sink. This backup feed water system is shown here. It's shown here to the bottom of this turbine building. However, this backup feed water system failed to operate because a block valve to the steam generator had been left closed because they were doing maintenance of this backup feed water system. So they isolated this system. This is the direct violation of the safety protocol because you cannot let the reactor to run with some of your safety system being offline. Because of that, the once-through steam generator dried of secondary water, causing the primary water coolant temperature and pressure to increase due to the loss of a heat sink. As planned, this high pressure appropriately triggered a pellet operated relief valve on top of the pressurizer to open, discharging vapor and liquid to a quench tank inside the containment building. So as shown here, we have the pressurizer. If the primary loop pressure is too high, it will automatically open those valves and discharge the steam into this quench tank to condense. In addition, this high reactor coolant system pressure also scrammed the reactor, so the reactor has been emergency shut down, with control rod being inserted into the core to stop the fission reaction and reduce the power. Until now, all the systems behave normally as planned. The reactor coolant system pressure dropped to normal within about 13 seconds, and this relief valve should have closed. But instead, it stuck open and remained open for 142 minutes. So here we have a mechanical failure of this relief valve and this valve stuck open, causing a small loss of coolant accident, small LOCA. Unfortunately, the reactor operators were unaware that this relief valve stuck open, because an indicator on the control panel implies that it has been closed. That indicator only indicated that the system has commanded this valve to close. However, the actual position of this valve will be unknown. The escaping primary coolant eventually filled the quench tank that in turn released radioactive water to the contaminated building floor, trigger another alarm to the operator. So the operator will know that the temperature inside this contaminated building is increasing above a certain level, and also you have the radiation alarm because those water are highly radioactive. So the reactor primary system continues to lose water. About 2 minutes into the accident, the pressure dropped to the set point to trigger this high pressure ECCS to activate, because you have reduced the reactor coolant system pressure. However, the operator thought the pressurizer was filling with water, and they manually reduced the ECCS flow dramatically 2 to 3 minutes later. Because the operator do not want the pressurizer to completely filled with water. Therefore, they do not want the primary loop to have too much water. The operator makes such false judgment because that the water is being boiled inside the core, and those steam pushed the water into the pressurizer, and causing the pressurizer water level to rise. This figure shows the 3 Mile Island control room simulator. So in the real control room, the control panel will be identical to this simulator. Then the core heated up and became uncovered as the primary coolant boiled away. Boiling within the core exacerbate operator confusion because steam bubble formation displaced water into the pressurizer, increasing the pressurizer water level and giving the operator the appearance of adequate coolant inventory. The decay heat caused major field damage, including melting and hydrogen production. Later, the reactor coolant pump were also shut off for lack of liquid water, because if you have a bubble passing through those very big pump, it will cause the vibration, and that vibration may damage the piping. Therefore, those primary pump has to be shut off. The water released from the quench tank collected in the building sump, and about 8,000 gallons were pumped to the auxiliary building, where the radioactive waste tank filled to the point that the rupture disc was blown and water was spilled onto the floor, releasing radioactive gases. So first, this quench tank is full, so the water will flow to this contaminated building sump. Then this radioactive water is pumped to this auxiliary building into this reactive waste storage tank. Then eventually this tank is also full, so those water is spilled into this auxiliary building. Now it is outside this contaminated building, and the radioactive gas will be released to the environment. A second release point was the dissolved gas in the primary coolant, which was removed through the let-down line. So you can see that there's a purple line, and the primary loop water is discharged here. and those water are placed in the makeup tank. The gases in this makeup tank were transferred to the waste gas tank system, or transferred into this waste gas tank system. This one also has a leak. The radioactive xenon and krypton, as well as a small amount of radioactive iodine, passed through ventilation filter and were detected outside the contaminated building. The radiation dosage to anyone was estimated to be less than 100 mg or 1 millisievert. The average exposure to people within 50 miles was estimated to be only 1.5 mg or 15 microsievert. This is less than that caused by a medical X-ray. The 3 Mile Island accident was due to a combination of design efficiency, inadequate control of water and insufficient instrument, and 2, equipment failure, the stuck pressurizer valve, and 3, operator error, especially turning off the ECCS system and also the pumps. A recovery program for 3 Mile Island was later initiated. The interior of the reactor pressure vessel was examined by use of miniature video cameras attached to the end of long cables inserted from the top. The damage, as illustrated by this figure, was greater than originally thought. A significant region of the core, the upper 5 feet, was missing. They were melted and slumped into the portion below, and solidified molten fuel was also found in the lower part of the vessel. You will see that at the lower region of this reactor pressure vessel, there are molten fuel. Special handling tools were devised to extract the damaged fuel. Care was taken by measurement and analysis to ensure that the debris would not go critical during recovery. The fuel was transferred to a series of always safe canisters for storage and shipment. The second accident in human history is Chernobyl accident. This is one of the worst nuclear accidents in the history. It is rated as the highest level in international nuclear event scale level 7, so that's the worst accident. It occurs in 1986 currently in Ukraine. This power plant has 4 reactors, and the type is RMBK 1000. Each of the reactors is capable of producing 1 gigawatt of electrical power. In other words, the thermal power is over 3 gigawatts. And 4 of these reactors produce 10% of Ukraine's electricity at the time of the accident. Currently, all 4 reactors has been shut down. The top figure shows the location of this Chernobyl nuclear power plant. The bottom figure shows the monument at the present day. Behind this monument, you will see that the reactor is covered with a concrete shell, and inside this concrete building, that is the damaged reactor. This figure shows the basic configuration of this RMBK 1000 reactor. This reactor is specially designed. It is boiling water reactor because the water is boiled inside this core and produce the steam. So this reactor uses multiple fuel channels, and the fuel is located inside each of those fuel channels. Then the steam will be collected inside this water steam separator. Then the dry steam will be sent to the turbine and rotate the generator to produce the electricity. Then the wet steam will be condensed inside this condenser. Then the liquid water will be sent back to the core for another boiling cycle. The reactor uses the coolant channel because the moderator is made by the graphite. So this reactor is graphite moderated. So you have the graphite surrounding each of those fuel channels to slow down the neutron. This reactor is of early generation 2 design, and it is one of the oldest commercial reactor design still in wide operation. Now we have another figure from the book to show the design of this RBK reactor. This reactor is evolved from the Russian defense reactor. It has the online refueling capability. It means that to refuel this reactor, you don't have to shut down this reactor. You just need to isolate one of the fuel channel and refuel that fuel channel. So the core was cylindrical, 7 meters high, 12 meters in diameter. Moderator graphite blocks were pierced by vertical holes to hold this 8.8 centimeter diameter pressure tube. Each tube contains multiple slightly enriched UO2, 2% enrichment, enriched UO2 fuel rod, and ordinary water coolant that underwent boiling. Similar to many coal-fired power plants, a steam drum separated vapor from the coolant existing in the core and recirculated the liquid component back to the reactor. Now let's dive into this accident. Before this accident, the reactor was working at the full power normally. Then they decided to conduct an experiment. So an experiment related to the capability of the turbines to supply electricity during coast down in an emergency was being performed. They want to learn after the turbine is tripped, then the turbine rotation will be slowed down. They want to know if this rotational energy can be used to supply the electricity used for other safety system. So they decided to conduct a real experiment. So the operator were under pressure to complete this test because the next available maintenance period was more than a year away. Okay, if they miss this window, then they will wait for another year. Then the power was to be reduced from 3200 megawatt thermal to approximately 700 megawatt thermal. However, the operator allowed the power to drop to 30 megawatt thermal, so the reactor power was reduced too low. At that point, the neutron flux was too low to burn out the accumulated xenon-135. So from the previous chapter, we know that the xenon-135 is poison. And if the power is too low, you have too less neutron to burn this xenon-135, then it will accumulate in the core. So the buildup of this absorber made the reactor very difficult to raise the power, and only 200 megawatt thermal could be reached. Based on the protocol, safety protocol, if the reactor power is too low, you will have to wait several days in order for this xenon-135 to decay out. At that time, you can restore your reactor power to normal. However, they decide to break the law. So in violation of the rules, most of the control rods were pulled out to maintain criticality. Then the coolant flow was reduced to a value at which steam wells were created. So they withdrawn too many control rods and also reduced the coolant flow rate and caused the steam bubble formation inside the core. The steam bubble formation decreased the water mass, so you have more bubbles, then you have less water in the core region. And the water will absorb the neutrons. Okay. So you have less water, you will have less neutron absorbed by the water, and concomitantly raising the neutron flux. You have higher neutron flux, you have higher power, thermal power. So this, because this over-moderated RMBK had a positive void coefficient of reactivity, in contrast with that of light water reactor, in which the reduced coolant mass would have a mean less moderator percent 2. In other words, this one has positive void coefficient. So you have more steam, you have higher power, which is undesired. The positive reactivity feedback initiated by steam void formation caused the power to flash up to 30,000 megawatt thermal. That is 10 times of the operating level. It is off the chart. The power could not be reduced because the control rod were too far out to have an effect. About 1 minute passed from the start of the experiment to the runaway reaction. The large energy release caused the physical disassembly of the core, thereby terminating the fission chain reactions. This excess energy pulverized the fuel, caused the steam pressure to build, and ruptured the coolant tubes. The steam and hydrogen explosion blow off of the roof of the building, housing the reactor, and released about 360 megacurie of activity, including cesium-137, iodine-131, noble gas, and other fission products. A radioactive cloud passed over several countries of Europe, but activity was detected worldwide. Food crops had to be discarded because of contamination. A total of 237 operating personnel, firefighter, and emergency workers were initially hospitalized with radiation sickness. 28 of them died from acute radiation syndrome. Their exposure ranged from 2.2 Gray to as high as 16 Grays, and the lethal dose is about 4 Grays. However, different people will have a different reaction to the same dose. Thousands of people were evacuated. Many of them were permanently relocated with great cost and undoubtedly much distress. In summary, the primary cause of this Chernobyl accident, first, is that the reactor is poorly designed. This reactor type is inherently unsafe and should be phased out. Second, the reactor safety protocol should be strictly followed. Next, we will calculate the example 21.6 about the Chernobyl reactor. So this Chernobyl reactor is assumed to experience two peak powers during the accident. The first peak was stopped by the Doppler field temperature coefficient. We introduced this one before, so that is negative feedback. The alpha field is equal to negative 1.2 times 10 to negative 5 per degree. Okay. Using the delayed neutron fraction beta of 0.0048, the fuel temperature increase can be estimated from the compensation for the positive reactivity insertion of $2.5. Then for our previously introduced equation from the previous chapter, the reactivity rho is equal to alpha times the delta T. Then we calculate delta T, so we move the alpha field to the right hand side. So delta T is equal to rho over the alpha field. Rho is the activity. And here we have the activity that is 2.5. So we need to compensate this positive reactivity insertion of $2.5. Therefore, from this negative feedback, we will have to produce negative $2.5. So here we have a negative sign here. Then $1 is 1 beta, that is equal to 0.0048. Okay, then divide this alpha field, that is negative 1.2 times 10 to negative 5. So result is 1000 Celsius. This problem means that you have $2.5 of positive reactivity insertion. Then it will cause the fuel temperature to increase. It will give you higher power than fuel temperature is going to increase. Then higher fuel temperature will in turn give you the negative reactivity insertion. So after your fuel is increased by 1000 degrees, then this positive reactivity insertion of $2.5 has been compensated by this Doppler fuel temperature coefficient. The last notable nuclear accident is Fukushima Daiichi accident. This one is also rated as level 7 in the INES scale. It occurs recently, 9 years ago, in 2011. And the location is the east coast of Japan, so as shown here. The reactor is a boiling water reactor as well. And the major cause is the beyond the design basis accident. So the reactor suffers station blackout that is caused by earthquake and tsunami. So the consequence is that 3 out of the Plant 6 nuclear reactor were melted, and also there's a release of substantial radioactive material. On March 11, 2011, a multi-unit accident occurred at the Fukushima Daiichi plant on the northeastern coastline of Japan. In the afternoon, there was an earthquake, a seismic event registering 9.0 scale, struck 70 kilograms off the east coast, resulting in an automatic shutdown of reactor unit 1, 2, and 3, which were operating at the rated power at that time. Unit 4, 5, 6 were shut down for refueling. The earthquake caused the damage to the nearby electric power system, resulting in the loss of offsite power. But on-site diesel generator was started to supply equipment such as decay heat removal system for this 3 boiling water reactor, which began operation in the 1970s. Approximately an hour after the earthquake, a tsunami of about 13 meters in height inundated the plant site. You can see that from this figure, from the bottom figure, you will see that the reactor is only about 10 meters above this sea level. So this 13-meter tsunami is able to reach this power plant. The resulting flooding rendered the emergency diesel generator and other required electrical switchgear inoperable, because those diesel generator was located in the basement. So this is not a good design. Thus, the plant experienced a station blackout, which is the loss of both on-site and off-site power. At this point, only the Unit 3 DC batteries were supplying its instrumentation and control systems, but sufficient power were not available for large equipment such as pumps. Although the reactor has been shut down, the fission product decay heat requires large heat removal system. This figure shows the basic design of this General Electric BWR with Mark I containment building. This purple color is the containment building, that is primary containment. And the reactor core is located at the center of this containment building. You see that this primary containment looks like an inverted light bulb. If there's any leak inside this primary containment building, inside the primary containment, then those steam will be collected and pushed into this white well. This white well has a shape of a donut surrounding this primary containment. It is filled with water, cold water. So when the hot steam in contact with the cold water, it will be condensed in order to reduce its pressure. The Unit 2 and 3 featured a reactor core isolation cooling system, RCIC system. So this RCIC pump is driven by steam from the reactor to provide makeup water when the normal cooling water supply is unavailable. You can see that this system is designed in this way. So you have the steam produced from the core. Then this steam is used to rotate this small turbine. Then the white steam will be sent to this suppression pool for condensing. Then this rotation will drive a pump. This pump will take the water from this suppression pool and send it back to the core for continuous cooling. Liquid water from the Toredo white well is pumped into the reactor, while the vapor exiting the reactor through the RCIC turbine is condensed in the white well to suppress pressure. However, the requisite batteries for this system to function will eventually be depleted. In addition, this closed system has no capability of dissipating its heat beyond ambient heat loss mechanism. So, without the heat dissipation, the coolant pressure in the reactor increased as decay heat continued to produce steam. Relief valves opened to discharge steam into the white well and reduce reactor pressure. Without the introduction of more water into the reactor, the liquid level in the vessel descended and the top of the core was no longer submerged in the liquid. If the core is no longer being cooled, the cladding and the fuel began to overheat, releasing gaseous fission product and hydrogen into the reactor vessel, which eventually passed into the wet well and later the dry well atmosphere. Over the next few days, the core damage occurred to reactor 1, 3, and 2 in the order. The steam and released gases drove up pressure within the primary containment. Rather than allow the containment to rupture, the operator had to partially depress the system, which resulted in the venting of radioactive fission product and hydrogen into the upper floor of the reactor building. The flammable H2 exploded, thereby destroying the steel frame structure of the Unit 1, 3, and 4 reactor surface level. These two figures shows the suspected location of the molten fuel inside Unit 1 and Unit 2. You can see that most of the fuel has been melted. For Unit 1, it suffers the reactor pressure vessel melting through. So you will see that the molten fuel is laying on the concrete floor. But for the Unit 2, situation is slightly better, and the fuel is partially melted. You have some of the fuel intact. However, it is also suspected that the Unit 2 reactor pressure vessel is also melted through, and you will see the fuel on the concrete floor. Next, we will use the example 21.7 to conclude this chapter. In this example, we are going to study how much time is needed for the decay heat to melt the fuel. Okay. So example 21.7. The earliest time at which fuel melting begins in Fukushima Unit 1 can be estimated from the thermal energy needed to raise the UO2 fuel temperature from about 300 Celsius to 2800 Celsius. And we know that the UO2 fuel mass is 77 metric tons, and the specific heat of this fuel is 0.25 kilojoule per kilogram per Celsius. So the concept is that the fuel is going to produce the decay heat. Then, if the reactor loses cooling, then those heat has nowhere to go and to be stored inside this fuel. And if you have the heat stored inside the fuel, then the fuel temperature is going to increase. And the first step is that we'd like to calculate how much heat or how much heat energy this fuel can store before it is melted. Okay, so from the 300 Celsius to 2800 Celsius, how much heat can be stored inside this fuel? This can be calculated from this simple equation, okay, specific heat equation. We have the Q is equal to MC times delta T. Here the Q is the total heat stored inside the fuel. The M is the mass of the fuel. C is the specific heat of the fuel. Then delta T is the temperature increase of the fuel. In this case, we have 77 metric tons. So 77 times 1000 kilogram. Cp is given 0.25 kilojoule per kilogram per Celsius. Then the temperature increase, we increase the temperature from 300 Celsius to 2800 Celsius. Then we get 4.8 times 10 to 7 kilojoule. It means that before the fuel is melted, it can store 4.8 times 10 to 7 kilojoules, this amount of heat. Then we will calculate how much time is needed after the reactor shut down. The reactor can produce this amount of heat. Okay. We know that we have the reactor decay power equation, which is this one. So we have the power as a function of time. If we integrate the power formula, we will be able to determine the total heat produced, because the power times the time, you will get the heat. Then we integrate this power, because power is a function of time. We get a total heat produced within a certain period of time. So now we assume that this reactor has a thermal power of 1380 megawatt before the shutdown. And the reactor has been operated for infinite amount of period, so that we will have this simplified equation. Okay, this simplified equation. We will also assume that the cooling of this reactor stopped 1 hour after the earthquake, because the earthquake will take some time to reach the plant. Okay, we'll assume that the time period is 1 hour. Then we calculate the total amount of heat produced within a certain period of time. So the total heat Q is equal to the integration of the P. So the heat is equal to the integration of the power, and it is from 1 hour to certain time, which is unknown. Okay. Then we replace this 1 hour by 3600 seconds, because this decay power equation only uses the seconds as a unit, as a time unit. So here we use a different variable, the tau, as the integration variable. Okay. So this is the power function, and the integration of this one will give you the analytical solution, okay, which is this formula. Then we evaluate this formula at t and also at 3600 seconds, and we do a subtraction. So we get the final equation here. So from 1 hour to certain time t, the total heat produced will be this formula. Then we will let this Q to equal to 4.8 times 10 to 7 kilojoule. Okay, we just equate these two equations. And also we replace this P0 by 1380 times 1000 kilowatt. Then we solve for the T. Okay, solve for the T. So the T result is about 1.75 hours. This one means that after the tsunami hit this power plant, you will have only 0.75 hours to restore the cooling before the fuel is melted. However, we have to say that this is a very conservative calculation, because we only consider the fuel that can store the heat. We neglected other material such as cladding and reactor vessel and other structure material, which can also absorb the heat and can slow down this fuel melting process. Okay, this is the last page of this slide, and we'll conclude this chapter. Thanks for watching.